So in this video we're going to look at another all-day time-lapse of the Sun taken with a hydrogen alpha solar telescope. And I did this yesterday because the weather was great all day and I was able to film the Sun from shortly after 7 a.m. right through until sunset. You may recall, almost 2 years ago I did a similar observation with the same telescope. What you will notice though is that the Sun appears a lot smaller in the earlier video than it does in yesterday's one. And the reason for that is because I'm using a different camera on the telescope. I'll talk about that more shortly. So here is the telescope and mount I used in the all-day solar time-lapse. The telescope is a Coronada Solarmax III 70mm hydrogen alpha telescope, specifically designed for viewing the Sun. The mount is a Celestron AVX equatorial mount. I've had it for over 3 years, and recently I just pulled it apart to reset the gear mesh just to remove any play in declination and RA. So that mount is again working just like new. And the telescope has a dual speed rack and pinion focuser which allows you to focus it very precisely. For coarse quick focusing you use this black knob, and then for fine tuning you use this gold knob. The camera is a ZWO ASI 183 MC color camera. It is a perfect match for this telescope as it is one of the highest resolution cameras that ZWO makes, and at 4K resolution the Sun is framed nicely. So when you first start using a dedicated astronomy imaging camera on your telescope, the choices can be quite overwhelming. There are numerous different models, each with different specifications and sensor sizes. And it can be quite difficult to understand which is the best camera to buy for your specific telescope. So aside from choosing which telescope you need, you also have to get a camera that is going to match the telescope to give you the results you desire. Now in my earlier observation, I had a 294 MC camera, which is a great camera on a powerful telescope, but on the Coronado, with a focal length of only 400mm, the field of view is quite large, and that is why the Sun appears small. To help decide what is the optimum camera to use, we have this field of view calculator on the Astronomy Tools website, and I'll show you how we can use that now. So this field of view calculator allows you to test various combinations of telescopes and astronomy imaging cameras on different targets to see how the field of view is going to frame your object. If you select the wrong camera for the telescope, you could be quite disappointed with the results. Here I have selected the Moon, a Celestron 9.25 SCT, which is my largest telescope, and if we choose a camera with a very small sensor, what we're going to see is only a very small portion of the Moon. Here we have the ASI 120, which has a very tiny sensor. You can see that the focal length of the telescope is 2350mm. Now if we add to the view, this is going to show us what the Moon will look like with that combination. As you can see, the magnification is too great. You can't see all of the Moon. If we choose a very different camera with a much larger sensor, something like the 294, we add that one to the view and we remove the original one, you can see a lot more of the Moon. To see all of the Moon, we're going to have to go to a lower power telescope. Something like the Skywatcher ED80. And there you can see all of the Moon. Now that's probably too small, so again we can try different cameras. And with the ED80 I found the 183 works very nicely. So it's a very useful resource to help you decide what is the optimum camera to use for the various different telescopes. In addition to that, when you select the camera, it will default to the maximum resolution the camera is capable of. If you have an extremely high resolution camera, such as the 183, you can set the resolution manually in the software. And if we set that to 3840 by 2160, which is 4K resolution, and add that to the view, you can see it is just about perfect. And that is the combination that I used in my time lapse. A 400mm focal length Coronada telescope with an ASI 183 camera set to 4K resolution. And that's what the frame looks like. And there you can see it's pretty close. So I'll play the time lapse in full at the end of this video. It goes for more than 10 minutes, but I just want to explain a few points. The camera was taking one photograph every 2 seconds all day, and that was compiled into a time lapse at 30 frames per second. As the sun was getting close to setting, I changed the capture rate from 1 frame every 2 seconds to 2 frames every second. So it was 4 times faster. And you'll see that as a definite slowdown in the movement of the clouds as the sun was about to set. Additionally, this timestamp is in UTC. So to get the local Sydney time, you need to add 10 hours. So for example, when you see 0033, that's actually 10:33 local time in Sydney. Now what you'll notice occurs just after local noon, around 12:07 local time, is a meridian flip. And I have discussed the meridian flip previously. Let's take a quick look at it now. So in a previous video, you may recall I described what the meridian flip was and why it is necessary on many equatorial mounts, depending upon the design of the mount and the size of the telescope. If we're tracking the sun, this mount is moving at a steady 15 degrees per hour. So after 6 hours, it's going to change orientation by 90 degrees. As the sun crosses the meridian, the telescope is going to be in that orientation, and as it continues to track the sun in the afternoon, there is a possibility that the telescope will impact the base of the mount, which it has done there. Now, to prevent that from occurring, what the telescope does is a meridian flip. So when it reaches this point, when the object crosses the meridian, it will reorientate itself, swapping the declination and the RA axis by 180 degrees to pick up the object again in this orientation. And that way it can continue tracking with the telescope well clear and above the mount. Now this little ioptron mount will do an automatic meridian flip. This one, the Celestron, it won't. I had to do that manually shortly after the sun crossed the meridian. Now if you don't do anything, it'll go to about 20 degrees past that and then just stop, and it just won't track any further. So as you'll see in my video, the meridian flip occurs shortly after local noon. Now one point to note is the orientation of the camera on the telescope after it does the meridian flip. I have set it up deliberately so that the orientation of the camera is up in relation to the North Pole. So if we had the camera at the North Pole, it would be in that orientation. We can move it to any location on the Earth and keep it in the same orientation of up as we had at the North Pole. Now this is the whole point of an equatorial mount. It is to allow the telescope to track equal and opposite to the rotation of the Earth, and thereby keeping it pointed in one direction. And it also explains why the polar alignment angle varies by the latitude of your position on the Earth. At the equator, your RA axis is going to be horizontal because it is rotating in that axis. At Sydney, Australia, we're 34 degrees south latitude. You can see that the camera is still rotating in the same orientation that it would be at the North Pole, but now that is 34 degrees angled upwards towards the south. So as you can see, this camera is at the same orientation as it would appear at the North Pole. And that's going to have a very interesting result when the Earth comes into view as the sun sets. Try to imagine what angle you're going to see at that point. So if we keep the camera oriented in the direction of up at the North Pole and change latitude as we are filming a sunset, you will see the angle of the horizon as the sun sets changes according to latitude. As we move south, crossing the equator and into the southern hemisphere, it changes significantly. And from Sydney, Australia, at south 34 degrees latitude, when the sun sets and we see the horizon, it should appear at that angle. That is precisely what we do see because we live on a globe. And this is an observation I have been planning to do again for a long time. It was just a matter of being home with the free time and with the weather cooperating. Fortunately, yesterday they all came together, and my good friend Wes Wally was kind enough to send me a short clip of the image from Himawari 8 confirming that we had good weather in Sydney all day yesterday. Just one final point before playing the time lapse. You probably won't see it in the time lapse, but if you fast forward the 10 minutes within a few seconds, you can even see the very slow rotation of the sun itself. After the meridian flip, it appears to be rotating in the opposite direction because the camera has done a 180 degree orientation change. But there you can see, moving that slider back and forth, we are in fact seeing very slow rotation of the sun itself.